Okay, good morning. So this is last discussion. Uh, this is on uh, displacement method. So we could solve a torsion case by at least two methods. So first is we call the basic force method. So we are going to equaling the equations with the twisted angle and equaling the force, which is in our case is the torsion. And now we are going to use we call it displacement method. So we are going to equaling the torque with the twisted angle. Okay. And this is some constant that we are going to compute as well, the K and the small f, which is it's related to the inertia. Okay. So first, if we look at the equations, after we take the free body diagram and then we measure the torque equations, the second thing that we can do is we can measure the deformations. So the deformations, because of the NB is fixed, okay? So whatever happens in B, it doesn't really have any deformation in B because it's fixed. So we can assume that in this part, because this is a wall, that the angle or the deformation of the angle of B is 0. Okay. That means because material 1 and material 2 they are in the same length, and they are actually if one material got deformed, then the other material also deformed. So we could say that the material 1 and material 2 has the same deformation. And then this is actually the differences between the twisted on A and twisted on B. But since twisted angle on B is 0, then we could say that this is equal to only A. Okay, so now, because we already have all the components that I think we need to compute the rest of the computations, which is the K, the modulus multiplied with the inertia and divide by length. So we could first multiply the first material. The first material is the steel. Okay, so this is the steel. So steel G is 78 GPa. So we could write this is going to be maybe just like MPa, and then inertia. Maybe let me write inertia with this formula here. Let me write maybe down here. Maybe directly just right here. So for material 1, this will be pi 25 with power 4 millimeter 4 divided by 2. Check. So it's supposed to be 600,000. So this will equal 613.5 millimeter with power 4. And then for material 2, we take the R2 is 37.5. So 37.5. So it's going to be 2 million. So 2,492. 0.7 with power of 3 millimeter power 4. Now using that equations to calculate this K here, K1, multiply with 600,000 and divide by L. L is 0.5 meter, so it's going to be 500 millimeter. Okay. It's going to be 95706. Newton. This is going to be cancel this, cancel with that, and this is going to be millimeter per radian. Okay, and then we can take K2, 28,000, and then multiply with that. Divide by 500. Is going to be 139. 1.2. This is per radian. And then we are going to take this K into our displacement method here. So we are going to write maybe down here. So we say that we take T1 is K1 twisted angle A based on the deformations we have here, and then we say also the torque 2 is K2 also deformation A. Okay. So we can say that the A is this is from, oh maybe let me write here, T1 plus T2 is the A. Okay. So from this equations we can write the displacement is equal TA over K1 plus K2. So TA is 350 Newton meter. Oh, I think we can change to meter from this millimeter here. I think maybe to make calculations much easier. So this will be meter, and this is now we take that into our calculations. So 350 divided by k. So 350. So 957 plus 1.4. So 1.487. And remember that this is still in radians. It's still in radians. So if you need to get into the angle, then you need to convert into the angle with pi, right? And the questions, that is for A, okay, the angle of rotations, right? Now for B, we need to determine the maximum stress, okay? Both in steel and in aluminum. And since we get the deformation for A, then we can rewrite for T1 and T2. Okay. So from this angle, we can write, let me write this. So T1 is the multiplication of the angle with the K. So we can multiply and we get that this T1 is 142.3 Newton meter and T2 is 207.6 Newton meter. Okay, we get T1, we get T2, then we can calculate the stress. Okay, so this is very similar to what we have before. So the torque is, you can see that the torque is actually like a force in our previous chapter. Okay, the elongation is like the twisted angle. Okay, so twisted angle we can think like elongations in our previous terms, and the stress, they are the same. So we are going to calculate the torque and the radius and the inertia, okay, to get this the stress. Okay, so let me write here. So sigma, or not sigma, the tau max. So for steel, the tau max is, we define the steel as material 1, right? So T1, R1, and then inertia. So all the terms we can calculate, right? If we calculate, this will equal to 5.8 around MPa. And then for the aluminum, this is T2, R2 divided by inertia. Okay. So all the component we have count already here, so we can just plug in and insert and find that this is going to be that. So we get this, the maximum shear stress. Okay. So first, you still need to draw, to visualize the free body diagram. And now we need to include the inertia, okay, the inertia for the hollow tube and the solid tube. This will be frequently happen, so you need to remember that. And you can choose between the basic force method or the displacement method. And then depend on the questions that being asked, whether it's asking the torque or maybe asking the tau max, then you could choose. Okay? Or if it is maybe asking the diameter that allowable for this kind of external torque, then you can just use the same principles, okay, and guidance to find the solutions. Okay, I would like to give you more examples here, but before that, just one more sections, small sections about the power transmission. Okay, so we are going to look on the power, which we define as a torque multiplied with the angular speed. So first is finding this relation first, okay, from the free body diagram, and you can go to inertia first, or probably go to this K1, K2 first, okay, and then you can go to the relations within these two to get a deformation angle or twisted angle. And after that, from this deformation, since we already have the relations, we can just multiply to find the torque, okay, and then we can find the stress, okay, from the torque. Okay, I think not really that complicated. Okay. So the key is, I think, understanding this part, this relation. After that, that's just inserting the formula. Okay, just use the formula as it. So remember, if they are like two materials, but they have inside the same shape, tubular shape, we could say that they are, when they deform, they will be deformed similarly. Okay, so their angle, their twisted angle will be the same. So you can say the angle for material 1 that is inside and material 2 will be the same. Okay, so we can take that as our assumption here. Okay, and since it's wall fixed in the wall here, we can say that the angle is 0. There will be no deformation at the end. Okay? So this is also important when you have two sides have a wall, then those two angles will be 0. So there will be only small change in the middle. Okay. All right. Okay, let me move to the new slide. Okay, you can check later. This one I will put into note later on after we finish all chapter 4. So this is the power transmission shafts. So if you see that the middle part is the shaft, okay. So this is a particular in like in the power plant, okay, or any fabrications that require some motor, okay? Like in the wheels of a vehicle, a car, okay. And they will have some connections, okay. And this is going to be it can depends on this torsion. It can also rotate and have some some work, right? So if you look here, we get torque, we get work, we get some deformations. Okay, so first we could write the general formula is described by work for D. This D. Okay, so work on D. We could say that this is equal to torque, and the deformations, that is going to be the deformation C, okay, because this is the one that is applicable here, right? And now if we see to the node C, we could see that we are going to have, so power at C, we can say P is derivative of the work, okay? And we can also think that because small change will happen in the angle, so that will be our approach for derivatives. So this will be equal to T and d dt of the angle. And this part here is our angular speed, right? Angular speed. So we have some angle, we have dt. So if we taken that into our definitions, that this is going to be equal to P equal torsion multiplied with the angular speed or angular velocity. This is power, this is torque. While the angular velocity, if you remember in physics, it stated that it is equal to the 2 pi with frequency. This is the rotation speed. So this is going to be equal to revolution, 1 revolution per second. So power is now in joule, or now it's watts, or joule per second, or let me write here, or joule per second. Okay, just that additional small section on power. Okay. So sometimes you need to compute the deformation or the torque, and then maybe the other question that might be asked is maybe compute power needs to make that deformations. This is like not really in the torsion, but it's like an accessories that might happen. Like in the previous chapters, we get the thermal deformations, right? That we need to add in the elongation part. Okay. This is also similar. And perhaps we need to calculate the power that that needs to deform some shaft with some angle and some torsion to calculate how much power it needs. And this is really important if you think in general, if you are building a power plant or working in an industry that needs to perhaps to save the energy. So perhaps choosing the ideal power plant or the ideal motor to get the efficiency or to get more power. Okay. Okay. Now, next part. Okay, next part. So, this is the power transmission shaft. Next part is the example. Okay, I would like to start with this. You can try to work on. I will give you how to solve this through the definitions, the basic definitions. After that, we can solve it directly. So first we see it's the same concept from the previous example as well. We see two material. So we have the core and the shell. Okay, so we have the core. Core is steel, and the shell is the titanium. Okay. So first we get the steel and titanium. Both have different modulus, okay, and they have different diameter as well. If the maximum shear stress in the steel is 50 megapascal, so for steel itself it's 50. What is the total torque applied to the bar? So this is the one that we asked. So we need to find the T, okay? And then what is the total angle, the twist angle? If it is the length is 2 meters. So first, let me remind you that if we look on the cross sections, so if we see, this is the steel, this is the titanium. Remember that if we take the, let's say this is the axis for the tau, and this is the density. We can see that this will be the maximum. Let's say this is the maximum for the steel. This is the tau steel max, which is the 50 MPa, and this will be the tau titanium max. Okay. So let me write again. G steel is 75 GPa. G titanium is 45 GPa, and then D, or maybe R, let me write R. RS is 25 divided by 2 is 12.5 millimeter, and titanium is 40 by 2 is 20 millimeter. Okay, the first relation that we can write is the tau. Let me write the general formula. It's density, and then the rate of change of the angle. And this part, the angle, assume constant usually, right? Now, based on this, we can write the ratio between the titanium and the ratio on steel. This is GT RT. This is GSRS. Now from these relations we can write, this is, if you don't remember, this is the shear strain distribution. Shear strain distribution. Oh, stress, sorry. Stress. And then we take the T max by some calculation from this ratio. This is equal to 45, 20 GPa, 20 millimeter. It's 50 MPa. All here, and then we can just compute, and this will be equal to 48 MPa. So from the tau equal G rho we can write this in terms of so take integral for this part. So this will be equal to so the angular change is tau divided by G and then multiplied by dr. So this will be equal 50 MPa. This is 75 MPa, and then maybe write 12.5 millimeter. So it's going to be 5.333 is radius per millimeter. Or if you would like to take into meter, you can just multiply. This is 5 multiplied by 1000 is 2. And then T, we could see T from the integration of rho, tau, and dA. And this is equal to the angle change, multiply with the G, and then integral of the rho squared dA from the AS plus GD integral, and we can simplify this and taken the integral, and this will be GS, and this, the rho and the dA, this will be the inertia. So this will be the inertia of the steel and the theta in titanium. Okay. So at the end you can go directly just for this inertia formulations. I would just like to show you how we relate to the definitions. So we take the inertia for steel is this solid, so we take pi over 2 r power of 4, 12.5. So 38349 millimeter 4. And for titanium, it's pi over 2 r titanium divided by r steel, because it's hollow. Okay, so we get 20 and multiply. So we get 21297.8 millimeter power 4. And then T now becomes multiplication for all this component, 75 GPa, or maybe we write it MPa. I think we can write on this side, or maybe just right here. I need to take this side here. This is rad over meter. So plus 45, and then multiply with after calculations, we get that T is supposed to be 665 Newton meter, and the total twist angle, then we take the change, multiply with the length, so 5333 multiply 2, so this will be 0.1066 radian. So this will be the answer. Actually, for number B, you can directly take that. You can just multiply the change in angle with the length. Actually, you could also remember that the angle, by the end of the day, if we assume that all the things with the regular assumptions, we can say that this is going to be this. Okay. Okay. Okay, I think that's it for today. So torsion finish. I will give you some exercise. I think we can have more exercise next. I think next Friday. So Tuesday we move to the next chapter, and perhaps if not next Friday, next 2 Friday, like next 2 weeks, maybe we can have another quiz with the torsion. Okay. Still considering offline quiz, but if I observe later on, if the schedule is not really good, then I think maybe online. Okay. Yeah, I think that's for today's class. Okay. Okay, and please wait um, the Moodle. I think I would like to give you assignments, okay, for hopefully for your to add your midterm score. Okay, so just wait. I think afternoon or maybe tomorrow morning. Okay.